My name is Daniel Lepkowski. I'm a PhD student in electrical and computer engineering under Professor Steve Ringel. And my project is on innovative pathways to greater than 30% efficient solar cells. So over 90% of the solar panels in use today are made of silicon, one of the most abundant and well understood material systems currently known. The problem with this is that researchers are currently approaching the fundamental limits of silicon solar cells. So what's the next technology that's going to bring us beyond our current limitations into this realm of high efficiency photovoltaics? One such technology is multi-junction 3-5 solar cells. The way these are made is they have multiple materials, each one absorbing a different color of the sun's light. This enables efficiencies that are roughly 2 to 2.5 times that of silicon alone. The problem with these is that they are produced on gallium arsenide or germanium substrates. These can cost up to $10,000 per square meter and are just way too cost prohibitive to be used in terrestrial applications. However, they're often used in satellites, so they're a very well-developed and mature technology. They're produced by a technique called epitaxy, which is the stacking of atoms on top of each other to form a single crystal that contains all of these different materials. So what if we could combine the best of both of these worlds? The low cost of silicon and the high performance of 3-5 multi-junctions. That's where our research comes in. We want to create this 3-5 silicon multi-junction structure where we start with a silicon solar cell and then we grow a 3-5 multi-junction structure on top of it. This could enable low cost and high efficiency devices. The problem with this is that the spacing between the atoms of the 3-5 material is different than that of the silicon. This causes lots of defects or dislocations to form, and these hurt the performance of our 3-5 top cell. That's where my work comes in. It's twofold. Reduce the density of these defects and understand the effect of these defects on our cell performance. So when I started here at Ohio State, we had a 13.3% efficient 3-5 silicon dual junction solar cell, and now we've achieved 21.8, which is a record efficiency for this technology. And we have a clear pathway with reduction in defect density up to 31%. This is actually a really important benchmark for commercialization. NREL, National Renewable Energy Laboratory, has identified 32% as a threshold in order to make this technology achievable. They state that with the appropriate scalability and reductions in cost of the substrate, that we can achieve 33 cents per watt, which is roughly 1/3 of that of current solar cell technologies now. So it's my belief that this technology is the future in low-cost, high-efficiency solar cells. Thank you.